Hi, everybody. I'm Katherine Freese, and I'm going to be talking about dark stars and the fact that they might already be in the data of the James Webb Space Telescope. Before I start, I did want to tell you about a new initiative that we have at the University of Texas in Austin in honor of Steven Weinberg. We now have the Weinberg Institute for Theoretical Physics, and we're just getting started. We're going to have many interesting adventures, and we hope that you will be part of them. So keep your eyes open for things that we're going to do. So the idea of dark stars, well, there was a movie that predated us called Dark Star, a cult film. But in 2007, the idea of dark stars in physics, that was something proposed by Doug Spolyar, Paolo Gondolo, and me. And since then, we've worked with a lot of other collaborators. And in particular, this work is done in collaboration with my former grad student, HeII, who is now a professor at Colgate University, and an undergraduate student at Colgate, Jillian Paulin. So I want to start out right away with the basic idea of dark stars. They would be the first stars to form in the history of the universe, and they would be powered by dark matter annihilation rather than by fusion. I have to point out, and I'll say this repeatedly, dark stars are made almost entirely of hydrogen and helium from the Big Bang, with dark matter constituting only 0.1% of the mass of the star. So they are made of atomic stuff, and it's dark matter that powers them. So to summarize kind of the basic picture of dark stars, they can last a very long time, millions to billions of years, which means they can grow to become very large, up to 10 million times the mass of the sun, and up to 10 million times as bright as the sun, which means they should be visible in the James Webb Space Telescope. And in fact, we have found candidates, so that's the whole point of this talk. Once the dark matter runs out, these giant beasts they eventually collapse to black holes, and they make million solar mass seeds for the big black holes that are seen throughout the universe. So they could be the origin of supermassive black holes. So that's the sort of summary for dark stars. So let me back up a little bit and give you the basic picture. They form at redshifts 10 to 20 in million solar mass mini halos. So these would be the precursors of galaxies, these mini halos that later merge together to make galaxies and clusters. And these stars form because you have collapsing clouds of molecular hydrogen right in the dark matter-rich centers of these mini halos. So as I said before, you have these collapsing clouds that are made of hydrogen and helium only from the Big Bang. But as they cool and they collapse en route to star formation, they pull in even more dark matter gravitationally. So you started out in a dark matter-rich region, and you pull in more dark matter, and then the dark matter, if it's its own antimatter, then the dark matter annihilation products would include E plus E minus photons, and these annihilation products would collide with the hydrogen in the cloud, and they'd get trapped inside the cloud and heated up. So at some point, the dark matter heating overwhelms any cooling, and that means the cloud has no longer the ability to cool and collapse, and that's the point at which a dark star is born, powered by dark matter. So that's the basic picture of dark stars. I'm going to take the rest of the talk to describe this in more detail, but let me go right to the bottom line of my point for this talk. The James Webb Space Telescope has found around 700 high-redshift objects with redshifts bigger than 10, and they assume they are quote-unquote galaxy candidates. However, as shown by Mike Boyle and Colchin and others, there's too many galaxies for LCDM. So it would be great if some of these were indeed dark stars, and that is a real possibility. So James Webb now has spectra only for 9 of these, because taking spectra is more difficult, and so far 5 are on the archive or published. Now, without spectra, you can't be sure of the redshift, but so of those 9 that you do know really are high redshift, specifically there is this JADES has 4 of these. It's a specific survey within the James Webb, and so those are the ones we studied, and our results are that 3 of the 4 high redshift JADES objects in JWST that we studied are consistent with dark stars. Okay, so I'm going to back up now to what dark stars are. So let me back up to the formation of the first stars with some nice pictures. So you have collapsing, you start out with dark matter that's starting to collapse, and then you have these molecular hydrogen clouds. Here we go, self-gravitating clouds. And normally they would collapse to little nuggets that later grow to make the population 3 stars. But the question we ask, what about the fact this happens in a really dark matter rich environment? And so in particular, the types of dark matter I'm going to talk about, for example, standard WIMPs, the standard masses in the GeV, TeV range, standard annihilation cross-section. I'm going to point out this is the same annihilation that leads to the correct WIMP abundance in today's universe, the same annihilation that gives potentially observable signals of positrons, gamma rays, and neutrinos, and so forth in searches for dark matter annihilation. Actually, it doesn't have to be WIMPs. Anything that deposits heat and serves as a heat source. And in fact, we found self-interacting dark matter can work just as well. So the dark matter heating is covered by a simple equation. So the annihilation rate would just be number density squared times cross-section times velocity squared, because you have 2 of these things hitting each other. And then the amount of heat you get out is roughly the full amount of mass of the WIMP. And so I multiply the rate of interaction rate with the amount of energy you get out. So there's the heating rate, which can also be written as energy density squared for the dark matter divided by mass times the cross section. And so I just want to point out that we will consider a variety of different masses, which essentially means considering a variety of different cross sections because of the way this scales. So we are not sensitive to any of the details. If that annihilation cross section is off by 3 orders of magnitude, it doesn't matter. You still get dark stars forming. Very insensitive to the details, which is really good news. Now, not all of the mass actually converts to heating because neutrinos can escape. So some fraction, maybe a third of the annihilation energy actually escapes the star, but the rest is a heat source. I wanted to point out that dark matter annihilation, because you're converting the particle mass to heat energy for the star, is damn efficient, almost 100% efficient. Fusion, on the other hand, is only 1% efficient. Only a fraction of the nuclear mass it turns into energy for the star. So dark matter power is really powerful. Another difference, fusion only takes place at the core, the center of the star, where the temperature is high enough. But dark matter doesn't care. It doesn't care about what the temperature is. So it actually takes place throughout the star, equal amount of dark matter power all the way throughout the star. So that's an interesting difference. Okay, so in order to make these dark stars, you have to have a sufficiently high dark matter density, because you have that number density squared in the heating rate. And so, yes, sure enough, we do. So you start out in a dark matter rich environment at the centers of this halo in early times, and you pull in more matter gravitationally. The baryons dominate the potential well, so they're pulling in more matter. They pull in more dark matter, and we treat that by an adiabatic contraction. So when you see the words adiabatic contraction, I'm just talking about gravitationally attracted dark matter. Later on, you could get more dark matter in there by capturing it if you have an additional ingredient, the scattering cross section. So that is another possibility. So I don't really have time to describe the studies that we made of stars. These are the first stars, and the density of hydrogen goes up in time. And as this cloud dominates the potential well, it pulls in more and more dark matter. And so starting from, it doesn't matter, you start from an NFW profile, a flat profile, doesn't matter. You're building up a big dark matter density. So then the second criterion for dark stars is the annihilation products get stuck in the star. Yes, they do. So here's something we could contribute as particle physicists that astronomers don't normally use, which is Pythia. We demanded 88 radiation lengths. These annihilation products are getting stuck. So that's something we were able to see. And the third ingredient is the dark matter heating has to beat the cooling. And yes, that happens. So yes, you have this new phase of stellar evolution, because here you go, you have this collapsing. The blue is the normal evolution, but here's this 100 GeV WIMP, for example, and when they cross, that's when the heating beats the cooling and impedes further collapse. So let me give you the basic properties of dark stars. They're big puffy objects. they can grow to be really large, really big in mass. All of them are large in radius. They're about 10 AU, and they can become very bright and yet remain very cool. So they're unusual big puffy objects. So the way we did this is we built up the mass starting with a few solar mass dark star, and then you find an equilibrium solution. The 4 equations of stellar structure are satisfied: hydrostatic equilibrium, thermal equilibrium. So then add on 1 solar mass at a time, always finding equilibrium solutions until you make very, very large first stars. So we did that, and I just want to show you again, look, baryon density is way bigger than dark matter density. So then these are the kinds of results we have. The brightness of the star overall here is dominated by dark matter annihilation until if you run out of dark matter field, then that goes away, and eventually you have fusion kicking in the smaller stars. This is an HR diagram to show you the surface temperatures of these things. For example, the 100 GeV WIMP with this purely gravitational dark matter, these things grow to be really large and they can keep growing. But while they're at it, they're still cool. This is like the surface temperature of the sun, not very hot objects. So not a lot of ionizing radiation coming off, which is why you can keep growing and growing. So there's an additional source of dark matter fuel, the same capture that happens in the dark matter direct detection experiments that people are looking for. And what happens next? Well, once you for some reason this dark star moves around and it gets to some region where there's not a lot of dark matter, then okay, eventually it will become a black hole. And if you have million solar mass seeds, you could explain all kinds of observed black holes, the ones in the centers of galaxies. And the big question is, how do you make billion solar mass black holes at redshifts of 6? Well, we can give seeds for that, which is pretty cool. Here we go. 10 to the 10 solar mass black hole at a redshift of 6. Wow. 800 million solar mass black hole at redshift of 7.5. We can help a lot with that. All right, so as far as observing dark stars, these are their spectra. And it's almost a black body, but you've got these lines from hydrogen and helium. And the James Webb Space Telescope can look for them. So look at this, the brightness, this is the sensitivity of different filters. And sure enough, that the objects stick out, the dark stars are visible. And you would see them as dropouts. In other words, you could see them in one wavelength band filter of the detectors, but not in another. And by doing that, that tells you the redshift of the object, because this cutoff is due to the fact that there's a Lyman alpha between the object and us, and it's swallowing the light. And depending on the distance to the object, the wavelength where that swallowing happens will depend on the distance to the object. So that's how you get the redshift. Okay, so as I said, we have these JADES, the JWST Advanced Deep Extragalactic Survey, JADES survey, has these 4 objects of interest, and we found that 3 of them are perfect matches for dark stars. So, and this is the redshift 13, 12, and 11. And the criteria to be dark star candidates, okay, the competitors, galaxies. Is it a dark star? Is it a galaxy? Dark stars are point objects, galaxies are resolved. The dark star spectra match the data. So we use the photometric data. And the third thing that would be great is, here's a smoking gun: dark stars predict a particular absorption line, which galaxies do not, this helium-2 1640. So the spectra currently are too noisy, but with longer exposure, this is something you could see, and that would be wonderful. So far, all of these JADES objects could be point objects, so you can't tell the difference. Could be dark stars, could be galaxies. The spectra, here we go, assuming a redshift 10 object. Well, here, these are the rest frame spectra of a dark star of various masses. And then zooming in, there's this line that you could see. Then what the Jillian did was she did an MCMC to optimize the chi-squared, assuming dark matter mass of 100 GeV for these 3 parameters: the mass of the dark star, its redshift, and magnification due to lensing. So maybe probably most people don't know the average magnification, the average line of sight is actually less than 1 because the big objects pull photons towards them. So anyway, when she did these fits, here's what she found. This is magnification versus redshift, and these are the best fits. And so sure enough, everything works. So the spectra, these are the data in black dots versus the predictions from these dark stars. And so we have three JADES objects. As I said, at redshifts, this was 13, 12, and 11 that match perfectly with the photometric data. Here's one in particular, the redshift 13 one, and these are the wavelength bands of the experiment, and it's a good match. So again, in these 3 criteria I talked about, the one that they're satisfied so far, and if we want to really differentiate from galaxies, we've got to look for this absorption line, which eventually you should have better spectra. So for example, here's an object that has great spectra. It's obviously a galaxy, says carbon, nitrogen, blah, blah, blah. But so these beautiful spectra are coming. Also wanted to mention that Roman Space Telescope, we've written in a very recent paper that these things are also visible there, and which has a much larger field of view, easier to find with Roman. So find them with Roman, then go study them with JWST, which goes to higher wavelength and also higher redshift. So in conclusion, dark matter can play a crucial role in the first stars by powering them, letting them also grow to become very massive and very bright, which means that they could be precursors to the supermassive black holes that are otherwise unexplained at high redshifts. And they might already have been discovered by the James Webb Space Telescope. That's very exciting, and are also detectable in the Roman space telescopes. So it is interesting to speculate WIMPs or SIDM, or who knows what their properties could be first detected by discovering dark stars. So people, give me a heat source. So we're now playing around with other heat sources to see what else might power dark stars. And I am now going to stop recording if I can figure out